Usually in a program, we've established that it's important to analyze how fast it runs. And usually it's not that hard. You just go through the program and see, okay, there's a loop here, so it's going to run n times. There's another loop, so it might run n squared times, etc. But a lot of times our programs will use a technique called recursion, as you guys know. And then it becomes kind of hard to analyze how long does this program take. That's because when you do recursion, you're calling the program again for a smaller value of the input usually. And so how do I know how long that takes? Well, then I have to know how long the new input takes, and so on, all the way to the bottom. But that gets pretty messy. Luckily, we have a couple of ways to calculate the runtime of programs that use recursion. Let's take a look at binary search, which we covered in recitation, but we'll go through the entire tree this time and understand the master theorem a little bit better. So as you guys remember, in binary search, we have some list in sorted order, and we have some target value. Let's say we want to find the number 5. So we keep a pointer at the front, a pointer at the end, and we look at the midpoint and what the value is here. Okay, maybe it's 3. If we know it's 3, then we move this pointer over and we just consider this half of the array, because we know that 5 is not going to be here because all of these numbers are less than 3. So we ask ourselves, how many steps does this binary search program take for a list of length n? Let's call that T of n. Well, basically all we do is we calculate the midpoint, look at that value. So that takes, 2 steps, which is constant time. But then we have to call another binary search on this new array. Now, how big is this new array? Well, this new array is half the size of n. So the number of steps it takes is whatever T of n over 2 is, plus 2, which is the number of steps we took, which is constant. So we don't really care about 2 versus, 3 or 1. This is what we call a recurrence. And in the exercises, you're going to be seeing recurrences like this one, where it calls smaller values and maybe does some overhead work as well. There's 3 methods to solving recurrences, which we'll cover. One is the recursion tree. The recursion tree gets generalized to the master theorem, so you don't actually have to draw out the tree each time. And then sometimes you get weird problems where you have to use the substitution method, which we'll use in one of the exercises. So here's how the tree vaguely works. Okay, we have this problem of binary search. Let's say we have, n. Maybe n is like 16 or something. How many steps does this take? Well, it's going to take 1 step here plus n over 2. And we have to call this binary search thing on n over 2 now. How many steps does this take? Well, this takes 1. And now we have to call, n over 4. And we keep doing this till we get to 1. And at each step, we take 1 work. Now we count up the total number of steps we take at each level of the recursion. So at this level, we do 1. At this level, we do 1, and so on. And at each step, we're halving it. So the height of this tree is log n. Log n times 1 equals log n. And that's how you figure out, using the recursion tree, why this takes theta of log n time. Of course, you can also plug it into master theorem, as we did in recitation, and get the same thing. So number 2, T of n equals 2 T of n minus 1 plus big theta of 1. So this program could be a lot of different things, but you can imagine it saying, okay, I get this input n, I do something pretty quick, and then I call the input on n minus 1, find out that answer, and I call it again on n minus 1 for whatever reason, and then get that answer, and then output whatever. So what's that going to do? Again, we start at the first layer n, and at n we're going to do theta of 1 work. Here though, since we're calling it twice, now we have an actual tree. And at each step here, we're doing theta of 1 work. So this is roughly 2 steps. Now for each of these, we call 2 times t of n minus 1 again. So we get n minus 2. And this is what's happening in your program. You're getting this recursion tree and calling smaller and smaller numbers. And we figure out how much work is being done at this level. Well, each of these things takes 1 step, theta of 1 step. So this is roughly 4. And then so on. We get all the way down to 1. And since our value is decreasing by 1 every time, the height of this whole thing is 2 to the n. And so we're going to get something like 2 to the n here. Now we just sum up the total number of steps it takes, 1 plus 2 plus ... plus 2 to the n. And we see that it's roughly 2 to the n plus 1, but that's big theta of 2 to the n. And you can see here that a lot of the work is being done at the very bottom of the tree, because there are so many nodes at the bottom of the tree, as opposed to the top of the tree, because there's only 1 node at the top of the tree, and you only do theta of 1 extra work besides the recursion at the top. Let's move on to number 3. In this recurrence, you're calling a smaller recursion twice with size n over 2, and at each step, you're doing roughly linear work in terms of the size. You might imagine you're doing something where you have a list of n things, you chop it in half, you do something to each of the 2 halves, and then you combine the 2 lists somehow by like merging or whatever. That might lead to a recurrence like this. Again, let's use the tree. We start at our original problem of n, but this time it's going to be calling n over 2 twice, but also doing an additional n work instead of 1, as we had in all our previous examples. In each of these, we're doing n over 2 work plus n over 2 work, which is n work total. And it's calling n to the 4. Each of these is going to be doing theta of n over 4 work. This becomes 4 times n over 4, which is n work again. And then so on until we have like 1 n times. And each step, we're doubling the number of leaves, but each number is halved, so we still do n work at each level. Again, this is halved every time, so there are log n levels. Each level takes n steps or n work, so this becomes n log n. Looking at these examples, we see that here the work gets bigger as we go down the tree, so the weight matters most at the leaves. And in these 2 examples, the weight is distributed equally among the tree. So each level kind of matters. You can imagine if this was O of n squared instead of n, then this becomes n squared. This becomes like n squared over 4 plus n squared over 4, which is n squared over 2. This becomes n squared over 4, and so on. And most of the work is actually done at the root of the tree. And we'll see why that's important momentarily. But not super momentarily. First, we're going to do 2 more problems to really drive home the tree example. Same deal here. Start with n. This is doing 1 work. We're recursing on n over 2. This is doing 2 because it's 1, 1. N over 4, this comes 4, and so on. Again, this is going to be log n size. And again, we're going to end up with the leaves having n leaves, each doing 1 work. So this becomes roughly O of n. And why is it n here? Because at each step we're doubling. So how many times do we double? Well, once we get to the root of the tree, we're doubling 2 to the log n times, right? Because the height is log n, so this is just equal to n. And we're summing, from 1, 2, 4 to n, so this is roughly 2n, which is big theta of n. Here, the weight is distributed at the bottom of the tree. We have n over 2, n over 4, and so on. And here, because we're only calling n over 2 once, we just get this sort of chain as opposed to a tree. So this, because it takes linear time, this is going to take n work, this is going to take n over 2 work, this is going to take n over 4, and so on. And here, notice that most of the work is done at the top. This becomes n plus n over 2 plus n over 4, which becomes 2n, which becomes, again, big theta of n. But now most of the work is being done here, as opposed to the rest of the tree. Now let's take a look at the master's theorem. Basically, the three cases correspond to whether or not the work is mostly concentrated at the top of the tree, the bottom of the tree, the leaves, or it's spread out evenly, as in the binary search. And this depends on, the relationship between C, which is the polynomial constant for how much work is being done outside of the recursion, and log base B of A, which is essentially how quick does our recursion split and how much extra work are we doing in the recursion. A quick way to see this is, let's say you have n and you have something like, let's say you have a general recursion. Well, how many things does it split into? It splits into A things. And each of these values is n over b. So let's compare the work being done at this level and the work being done at this level. At the top level, we're doing n to the c work. And at this level, we're doing A times n over b to the c work. So we're comparing n to the c and A times n over b to the c, which is n to the c over b to the c. So essentially we're asking ourselves, this value, A over b to the c, is that greater or less than 1? Is A greater than or equal to b to the c? Or, is c greater than or equal to or less than log base b of A? Right? If c is greater than log base b of A, then that means this is going to be smaller than 1, which means that there's more work being done at the root than the leaves. Or there's more work being done at the root than this level, which then continues onwards to lower levels. If c is smaller than this logarithm, then there's more work being done at this level than this level, because this value is greater than 1. And if they're equal, then these two are equal. And generally, if there's more work being done here, then there's going to be even more work done at the leaves. So all we care about is the leaves. If the work at the leaves dominates, then we just have to figure out how many leaves are there, which becomes n to the log base b of A. If the work at the root dominates, then the work at the root is all that matters. So the total runtime is n to the c. And if the work is balanced, if these two are equal, then the runtime is still this, but it's n to the c at each level, and there is generally roughly log n levels. So the total work becomes n to the c times log n, which is the special case 2 of the master's theorem. And that's why the master's theorem essentially works. You can derive it using the tree. But don't worry too much if you don't completely follow this, because in general, when you have this, you can just plug it into the master theorem blindly, and you'll just get the right answer. The last two exercises are pretty similar. You basically do the tree method again, and there's nothing super special. So we won't go over those. The last thing that we will do is problem 6 because it uses the substitution method, which is the last method we're going to use. So usually a recurrence will be something nice and you can just plug it into master theorem or use a recursion tree. But sometimes you get really finicky recursions like this. We can't plug this into the master theorem because it's not in the right form. And if we tried to do a recursion tree, we get something like this. Maybe kind of hard to see, but you just have all these random depths and it doesn't turn out super nice. You get all these like random nodes at different levels and it's hard to know, okay, what happens? How much total work is there? But if you kind of look at this and you cover it up like this, you could plug this into the master theorem and get something that's probably big theta of n. And like same here. And if you kind of look at it, we're calling n over 5 and 7n over 10. And these two, even summed together, are less than n, which is not that rigorous, but it gives you some reason to hope that in the tree, the work is going to be dominated at the root, as opposed to like all the leaves. So it's probably going to be something that's like theta of n, hopefully. And the substitution method gives us a good way of doing that. The idea is we make a guess for the runtime, and then we prove that it is true. So t of n is definitely going to be very small for small values of n. And we inductively show, if we assume that this is true, is big theta of n for all n smaller than this n, then we're going to show that it's true for n as well. So we need to show that there exists some constant c such that t of n is less than or equal to this constant c times n over 5, because remember we're using the inductive step. And this simplifies to this. Now if we do set this equal, remember we want the runtime of this to take c times n steps. If cn equals 0.9 cn plus n, we get the n's canceling out, and we get c equals 0.9 c plus 1, or 0.1 c equals 1, so c equals 10. And this is exactly the constant we want. Whenever c is at least 10, then we will have the fact that t of n will take at most 10n steps. And we can plug this in just to check. If t of n for all smaller n takes at least 10c n steps for small n, we can inductively show that this is true for big N as well. So let's plug in a bigger n. T of n is going to take how many steps? Well, it's going to take less than or equal to 10 times n over 5 plus 10 times 7n over 10 plus n, which is equal to 2n plus 7n plus n equals 10n steps. So we know that t of n inductively will always take at most 10n steps. And just to hit this home, let's say our guess was really bad. Let's say we thought this would be constant time. This is our guess. Then we're claiming that t of n is always going to take at most like c steps for whatever c. And this is true for even huge n. If we use the substitution step and try to prove this using induction, well, we're going to run into some issues. So plug in n over 5, we assume this takes less than c steps. We assume this takes at most c steps plus n. And if we set this equal, c equals 2c plus n, then we get like c equals negative n. And that's when you know you've like just definitely messed up, right? There's no positive realistic c. Is it true that t of n will always take less than c steps? You get like one of these extraneous solutions. So that's when you know your guess is wrong. But for your correct guesses, if you set this equal and you get a reasonable valid answer, you can go back and check and show inductively that your recurrence does have this specific runtime, in this case, linear time.